All right, so chapter 4. So we have various types of electrical drawings. Why? Because it depends on what you actually need to have in front of you to see it. So you have basic schematics. Those can mean any type of drawing at all because a schematic is just a what? What is the definition of schematic? It's a line drawing that is made for technical and scientific purposes. Okay? It's a very vague form of a definition, which means that that particular definition has a lot of overreach. We have wiring diagrams. We have electrical wiring diagrams, ladder diagrams, point drawings, and pictorial diagrams. Always depending upon exactly how much detail do you need about the connection points you're making. Does that make sense? Because if you just need something very basic, if you just need to kind of know how is this supposed to relate to this piece of machinery, supposed to relate to this piece of electrical equipment, I don't really need a complex drawing of here's how all the circuits are laid out. Something like a ladder diagram would work fine for that. However, if I'm trying to wire a house or a building, do I need to know where every switch, plug, and junction box should be? Everybody nod your head yes, because that is highly important. They don't need to know the logic of it. They don't need to know, oh, this is connected to this because of this. Most of the time, if you're an electrician going into a house and wiring it up, you don't need that. You just need to know where the homeowner wants the plug. Do you want it on the ceiling, on the floor, on the wall, where? Right? Versus, I've got this giant cabinet full of wires and spaghetti looking stuff. How are my contacts in this box related to my milling machine or what have you? On the other hand, there are sometimes you have to have a more complex drawing. Why? Because sometimes simple just does not give you a good enough picture. What do I mean by that? Well, if I've got something like a computer chip that's got 1,000,001 little legs, and yes, I do mean they can have a lot of legs. Just look at something like that. Something like this little computer chip right here. Do you think I really, really want to know exactly where each line should go to this sucker? Their answer is yes. I want to know where every connection's got to go because otherwise I could end up making the wrong connection, right? And that could be bad. That's the point where I'm going to want a very detailed drawing of everywhere this has to go to this chip. Which way it's supposed to face, all of that. So I do not install it wrong. Excuse me. So a circuit is a complete path for flow. That was something we emphasized Monday, right? A circuit is a complete path for flow. What do I mean by that? Well, that means that I have to have a source of all things power. So in electrical, that's a battery. It's Alabama Power, something. Something's got to give me a source. I have to have a path for that power to flow through. So these in electrical, it's wires. In hydraulics, pneumatic, it's hoses and pipes. And I have to have something at the very end of all of it to do something with it. Kind of like, what is the point of driving around in circles all day long, except that you're wasting gas, right? You could do it, but what is the point of it? All you do is put more wear and tear on your car. All you do is just make one big circuit. Generally, if you leave your house in your vehicle, you're going to go do something, right? There is a purpose to you doing something. Same thing for any circuit. It has to have a purpose for doing something. Okay? So you have a source, a path, and a load. A lot of circuits also include control devices. Why? Because being able to make it do something else every now and then is typically what we like to do. Having something that can do more than one thing, that's actually a pretty good idea. But something like electrical, you've seen it time and time again. A kid can build a very simple circuit with what? With what three materials can you build the most simplest of circuits in electrical?
Light bulb, conductor, source, power source.
Generally, it's a battery, a light bulb, and wire, right? Does it have to have a switch? No. Could I put a switch in there? Yeah. Actually makes it kind of nice because you don't have to maybe halfway zap yourself if you're pulling that wire on and off the battery, right? But is it required? No. Pneumatics and hydraulics, you can do the same thing. So if you have something at the very end that you just want to vent the air out of, that's fine. That works for pneumatics. You don't technically, and you only need this thing to blow something up or to drop it down. And what do I mean by that? I mean that they have these really cool things out these days that look like a little air hockey, that act like little air hockey pucks. That help move very big loads. Why? Because they're able to air it up and they can carry thousands of pounds and it only takes maybe 5 people to push it. Think about that for a minute. We can now lift and move thousands of pounds with maybe 3 people. All because of pneumatics. And the only purpose of these little air hockey puck pads is to inflate or de-inflate. Do I have to have a switch? I can just turn the compressor on and off. Hydraulics, you really don't want to do that just because hydraulics are pretty much the most biggest powerhouse we have. And those are something you really want to treat with respect. Hydraulics are very interesting. So with the power sources, we have an AC or DC source in electrical. What is AC, by the way? What is the definition of AC? It's an alternating current. So much like the waves at the beach, okay? It is alternating how far up and down it goes. Versus DC, which is more along the lines of a still lake. It's all still. It just keeps everything moving at the same pace, right? So pneumatics, we have compressors. That's pretty self-explanatory. And then hydraulics, we have pumps. Why do we have pumps? Just what it's called. But those are your sources. So, comparison of the wiring diagram versus the schematics. Wiring diagram should emphasize the connections between the different elements. Why? Because that is sometimes very vital. If I've got 2 pieces of equipment and I don't know how to put them together, a wiring diagram is very nice to sit there and go, oh, this is how they go together. Versus a schematic, which is just looking at the flow. Let me kind of sum this up real quick. Schematic is the most basic drawing you can have. All it's really trying to show you is start, middle, finish. It doesn't want to complicate it with a bunch of other junk in there. It wants a very clean looking diagram. Okay? So, wiring diagrams use lines to show connections. And the same goes for a schematic. Wiring diagrams can use pictorials that clearly look like the actual equipment. It might just use a symbol that is about as close approximation as you can. So, in other words, I could end up with something like this. Or something a little bit more complicated that is actually labeled and everything else and looks like the actual piece. They're both very similar, but one might give you a little more detail. That little notch right there is in a lot of different chips, or in most chips rather. And all it's just to show you is this way up. Okay. So schematics use symbols to indicate the function of the equipment and do not generally look like the actual equipment. Again, it's all about level of detail. How much detail do you need? How precise and what is the precision level that is necessary for this XYZ thing we're wiring up? Wiring diagrams should show equipment and wiring approximately as what they will look when actually installed. Now, approximate, why is that word in there?
Trying to get close to it as a kid.
Yeah, because what's the problem with most schematics? What's the problem with most drawings in general? They really, it's just like any plan in the world. No plan survives first contact with the real world. Was what I was trying to get y'all to think about. No actual plan survives contact with the real world. Okay? What do I mean by that? Well, let's say I've got this computer card. I've got to plug it up. My schematics say I should be plugging it over there, but I got a bunch of junk over there. I can't plug it over there, so I've got to find another place to plug it up. The plan does not show that I have to plug it up elsewhere, but because of reality, I had to. Same thing. Approximate is just about what everything is, just because, I'm gonna put it this way, just because an engineer says it's supposed to go somewhere, doesn't mean it can. The big robot we have in here, you have to have reinforced concrete, very thick reinforced concrete. If you don't have that and you can't put it in, then what do you have to do? Find somewhere else to put it. That's the honest truth. It happens a lot more than you think. Most buildings, the concrete is not that thick. We tend to think concrete is about this thick, right? No, most concrete is about yay thick. Why? It's more economical that way. So when you're trying to install some big piece of machinery that's going to do a lot of vibration and movement, that can cause you a lot of problems, right? Does the engineer always know exactly what the other engineers have done? No. Most of the time, the engineers aren't even aware there was another engineer before them. They might not have done it the right way, or that somebody might have cut corners. So approximation is key, and it's all about adaptability. Okay? Versus a schematic. So with a schematic, if I drew a schematic of, let's say, the piping in your house, from your hot water heater all the way to the last tap in your house, I could do a very close approximation, but could I be exact? No. If I'm just doing a schematic, do I need to be exact? Not really. Huh? No, you don't have to be that precise or really that much. You're just showing that, yes, there is plumbing in this house. The hot water heater's in the basement, not on the individual floors. So most electrical wiring diagrams use symbols and not so much pictures. Why? Well, because the more complex a drawing is, the more paper it takes up. And the harder it can be to trace things. Now, so if you make, not to mention, if you take all these symbols and start turning them into pictures of what they actually look like, you're going to end up with a very crowded page. Right? You're going to end up with a very overcrowded page. Is it going to be as easy to follow what you need to do if it's a very overcrowded page? No. And that kind of means that it loses its point. Now, if it's a piece of equipment that's really complicated, yeah, you might want to have that actual piece of equipment drawn out. Otherwise, signs and symbols work just as well. Because, yes, I can draw the symbol for a light bulb into my circuit. I could actually draw an actual light bulb. But it all depends on the fact that I can make this T90, I can make this actual size. But it just depends on what you're actually trying to do with that schematic. They often refer to diagrams that use symbols for electrical, schematics most often refer to diagrams that use symbols for electronic circuits. Like I said, schematics are very commonly used. Ladder diagrams show the logic of a circuit, and we've already kind of talked about that. We'll talk about it a bit more as we get on into this chapter. Pictorial diagrams use pictures of the drawing of the devices loads in a circuit. And blueprints or drawings use symbols and is a multi-craft term. Blueprint is probably one of the most common terms. Because think about it, what have you heard blueprint in conjunction with? Not just construction. Have y'all ever heard the term genetic blueprint? Yes, I know you have, because I know it's probably one of the biggest pop culture references these days, is everybody has a genetic blueprint. Whatever that's supposed to mean. What it means, essentially, is that your genetics are basically coded to build you. But it is a multi-craft term that spans not only construction and building, but also into science and technology. All right, so electrical wiring diagrams using symbols versus a basic ladder diagram. So a basic ladder diagram, you can see you've got the fuse, you've got your transformer, you've got contacts, you've got relays. But how does it actually work? How does it actually do anything? That's where something like this comes in. Yes, I know it looks really, really messy. But this is how most of these really do work as a actual wiring diagram. This is the simplified form. This is the actual guts of the machines. Okay, so you've got your motor, you've got your overload contacts, you've got all these contacts that work with them, your relay coils, disconnect switch, so on and so forth. This is the more complicated version of it. Now, if I do not need, back it up. If I'm trying to wire this up so I can install it, which one of these two do I need? I need the lower one, right? Why? Because it is showing me point-to-point connections to everything. Does that make sense? If I'm looking for something like a line diagram, I'm just looking for not so much the individual wires and how they're put together, but how is the system overall put together? What am I supposed to be looking at when I look at this system? Well, I'm supposed to know that if I energize relay coil F, that means that this guy right here will open, stopping this circuit right here from working, and this one will close, making this guy energize for as long as he needs to run. Does that make sense? If I'm looking here, not so much. I don't have to worry about, I'm not worrying about the logic of how it actually works. I'm looking at how is this thing actually wired so I can get this done and move on to the next project, right? So different things tell you different aspects of it. Because here's the actual components themselves. Would you want to draw out these components every time you had to do this? No. Gosh, no. You also have the problem of how are you going to draw your connections on something like this? They're great because they can show you, oh, this is your disconnect box. You have your transformer, your forward, reverse, and stop switches, your motor starter with your overloads, as well as your motor. And yes, I could somehow draw your point-to-point connections, but it's not going to be as easy as if you had the wiring diagram in front of you. Like I said, we mostly use symbols just because sake of ease. Not to mention, no, I'm not even gonna say that. Schematic. This is a very basic schematic. What is it showing us? It's showing us how the circuit works as well as what is connected to what. Now, does that mean that if I look at this actual circuit, that it's going to look exactly like this? It'd be nice if it did. No, generally you have this on a printed circuit board about 5 or 6 layers deep with all the connections on the inside of that circuit board. All right? If you're actually doing this outside of a PCB, printed circuit board, then you're dealing with something totally different. You're actually building the circuit yourself. Okay? Because that's what it looks like in actual life. Okay? I don't get to see all the wiring, do I? Not on something like that. Now why? Why don't I want to see all the wiring? Because, I'll put it this way, traces are very delicate. You don't really want them exposed to anything because if you have them exposed, what is the easiest thing to happen? Something comes along, scratches it, and that printed circuit board is toast. Because you cannot repair traces. It's impossible. So these typically are soldered on the back. But this isn't going to look anything like what it should, which is that guy right there. This is showing us how all the connections are made and how this works. This is the final product. Generally, if you look at a printed circuit board, which I don't know if I've got one in here. I'll have to find one. Basically, it says on these, this is an older one, but most of the newer ones will tell you what component is supposed to be where. This is where a resistor goes. This is where a diode goes, things like that. All right, so again, this is a ladder diagram. What is a ladder diagram meant to show? Is it supposed to show you point-to-point connections? Is it meant to show you all the loads in the circuit? Yeah, it's supposed to show you the loads. Does it show me how the loads are connected and work around and with each other? Yes, actually, because it shows me all my loads and how are they interacting with each other. So these right here, of course, are switches. These are the contact relays. You have an M3 that's going to go be paired with this guy down here. So in other words, whenever this guy disengages, because this guy engaged, the light will go out. That is the interaction here. If I trip M1, control relay 1 will start up because this contact will close. All right, so if I energize this guy right here will close, making this guy come on. Once this guy comes on, this guy right here will close, energizing this guy right here. Okay? This is showing you the interaction and playoff between all these components. That is the singular purpose of a ladder diagram. How are these components coming together? How do they work together? Does that make sense? Like I said, don't ever call that a wiring diagram in front of Rich Raymond. He takes a little bit of offense to that. Pictorial and line diagrams, again, so the whole point of a pictorial diagram is to what? Is to try and show you point-to-point wiring connections. Ladder diagram is just saying, okay, so you have to have a push button that goes to this relay. You have a second push button that's going to stop the whole system if it's pushed, that kind of thing. Okay? So which one's easier to see how it operates? The ladder diagram, the ladder line. Which one would be better to show you the actual physical connections you need to make? Pictorial. All right. So wiring diagrams. Some use pictures, others use symbols. It really depends on what the application is. You want to try and show placement of devices relative to the system, but is that always possible? No. Because if I'm trying to do a wiring diagram, and let's say a high rise of 50 stories, a 50-story building, you can't really do that as easily as what you would think. That's why most of those are diagrammed floor by floor. Why? Because I might need 20 plugs on the 50th floor and only maybe 5 plugs in the basement floor. All right? So then you have, again, the symbol for earth ground. Like I said, that is my biggest pet peeve as far as misused symbols. Why? Because it is the most misleading symbol misused. I kind of went into this spiel the other day, but I'll go ahead and say it again. Common means it comes to a common point. Earth ground means that you've got something put into the ground to drain off excessive charge. Okay? I'm not going to go into the whole spiel again. Just leave it at that. If you're using the symbol for earth ground, you need to have something that has a physical connection to earth ground. It needs to have a physical connection to the ground. Okay? What was one of the earliest things we ever grounded, by the way? Anybody know? What was the biggest problem they used to have way back before electricity was really put into houses? Most houses are made of what? Which is wood, which is very what? Very flammable. What you think about the weather we have here, all the lightning storms. There's a reason they invented the lightning rod. And what did the lightning rod do? Yep, the whole purpose of a lightning rod on a house or a business or anything else, and there's a big reason why they use it on a lot of high-rise buildings, because the higher you are, the closer you are to the sky, blah, blah, blah. So if you have a lightning rod, what it's meant to do is take all that energy and direct it to earth ground. Why? Because the ground can absorb a lot more electricity than our house can before it catches fire. That is one of the earliest uses of grounding that you have in that kind of an example. Okay? So we're going to go ahead and take back to it. This is a wiring diagram. How do I know it's a wiring diagram, guys? Because showing me point-to-point connections. Okay, that is the very biggest thing about a wiring diagram. It's showing me point-to-point connection. Okay, so if I've got a thermostat, it's showing me how each thermostat is connected to this side of everything. It's showing me my transformer. It's showing me a blower motor. You've got your limit switches, and it's using color codes to help you trace it. Okay, it's using color codes to show you where everything is made and break. So this one in particular is a floor plan drawing. Okay. What is it trying to tell y'all? This particular one, if I'm not mistaken, is the basic setup of the walls. Now, how can I tell that? Well, because as an electrician, you wouldn't need to know that this span of wall is 3 foot to, I'm sorry, I'm trying to read these in little small print and it's not working out for me. There we go. So this is telling you 15 feet 4 inches. This is telling you that this little pit right here is 9 feet 10 inches. It's telling you where the steel stairs are, the handrail is supposed to be. Basically, it's meant to do what it's doing, which is label everything. This one's also telling you how to run the, looks like it's showing you how to run the HVAC as well. Then you come up here, again, you're running whole spans of the room. That's what this one's trying to show you, is how everything is built. But is it telling you anything about electrical? Is it telling you anything about hydraulics or pneumatics? No. It's just telling you these are the different spans of this space. This would be the electrical side of it. How do I know it's electrical? How do I know this is electrical versus the other one? Because it's showing me connections and it's showing me plugs. I'm pretty sure that this is what it's showing you for electrical, for the lights, the fluorescent lights. For some reason that one coming to me today. But this is trying to show you the different electrical connections. Where does it go back to? It's showing you where a space heater is. It's showing you where lights are, showing you everything, right? Do I need to know wall spans for something like that? Nope. Yet hooked up to your sump pump and everything. So all this is showing you how the building is wired. Okay. Just trying to show how the building is wired. So this is a Dodge truck wiring diagram using pictures and its color-coded conductors. Looks a lot like spaghetti, doesn't it? But let me ask you this, could I still trace it? Yes. Because it's color-coded, I can start tracing. Let's say I want to start tracing this brown wire. Well, that's not very hard to do. All I got to do is just keep up with where it's going. And here comes some more brown wire, and it all goes to this guy right here, the ignition switch, and the clearance lamps. Now, it's showing me how everything is wired. Is it telling me how it works? Not really. It's trying to show me point-to-point connections, and that's something very much, that I need to know whenever I'm wiring this. If I'm wiring this up, do I really care how it works? Not really. Think about if you're the person having to wire this at the, this is a Dodge truck. If you're in Dodge, if you work for Dodge, do you really care how the truck is wired, or are you just trying to get it done as fast as possible so you can get it down the line? You're trying to get it done because you have a quota of the amount of trucks that you and everybody else in that line are supposed to put out for the day. If you don't meet that quota, you get in trouble. So having a basic showing of point-to-point connections works really well for this, right? I don't have to know that my ignition switch goes to everything and has to start off everything. I don't have to know where my spark plugs are all plugged into. I just have to know how to wire the individual parts. Okay? For this one, it's giving us a situation. It says that the horn will not work. So first of all, how do I locate my horn? Well, I'll start looking for it. Oh, here we go. These are my horns. So they're not working. I test the horns, they're fine. So what do I have to start doing? Start tracing my line. So I'll start going. So start tracing your line. Where is it going? Oh, it comes all the way back here to the horn relay. Huh? Might have a bad relay. I have a secondary horn right here. I'll line it in a different color here. So I'll start following it. It looks like it goes the exact same place. Back to that relay. So I might need to check the relay. But the relay's fine. So then I start looking here. Maybe my button is bad. Right? So that's how I figure out how is this wired? What could possibly have gone wrong? And where is this wired to? Okay. So let's say looking at this, it's very easy to tell where things lead to and from. You have your headlamps. Those have their own junction boxes. They both have parking lights, and they all go back to your selector switch. Okay? This all in here is on the inside of the car, if I remember right. But you've got a beam indicator, which is supposed to tell you, the owner, hey, your lights are on. Right? You have your fuel tank unit, your license plate light, your dome light, everything connects. And if you ever have to troubleshoot, knowing what that connection is, and just about make things a lot easier when you're trying to trace things down. Because if you open up anything electrical, what do you always end up seeing? First, huh? wires that look like what? Yeah, it looks like spaghetti town in there, right? Looks like somebody boiled a bunch of pasta and then just like whack. You know, that's the whole thing, is that wiring diagrams are supposed to show you this is connected here, this is connected here, and it tells you generally, most of the time, that this is this color wire, this is that color wire. Why? Because if you're in spaghetti town and you're trying to figure out just why my horn relay's not working and where does it go exactly, makes it a lot easier when you can start tracing by color. Right? Becomes a little less spaghetti town whenever you have the right way to read it. Because what did I tell you at the beginning of this class? Is that basically what you're learning is a new language. This is truly a different language and a different way of reading a language, right? So you have a 240 volt outlet, you have a hot, neutral, a second hot, and a ground. Versus your basic where you have a hot, neutral, ground. Why do we have a different kind of plug for a 240 versus a 120? Exactly. 240, we don't want to plug something 120 into a 240. That would end up being something along the lines of Tom and Jerry, where your cat plugs something in, or one of the characters plugs something in and they get shocked. Yeah, that's going to burn through your appliance real fast to put a 120 in a 240. Don't do that. So, has anybody ever had to change out their own thermostat before? What's that? Anybody? Nobody?
In the car?
No, in your house. It's not that hard, right? Why? Because basically, they literally tell you black wire here, white wire here, red, yellow, blue, green, that kind of thing. It's really not that hard. I've helped my dad do it a few times now. They quite literally give you an instruction manual and say, if you have this color wire, it goes here. If you have this color wire, it goes there. This color wire goes here. And you're done. They give you a wiring diagram and you just sit there and go, oh, done. Okay. You have three-way switches to carry multiple lights. Okay. Just kind of keep moving here, guys. So series and parallel circuits. So series circuits used to be a big thing. They're not so much anymore. One of the main examples you can think of for series circuits these days is what? And even those are changing. Christmas tree lights. One goes down, what happens to all the other lights in that string? They all go out. But these days, it's not so much true anymore, is it? If one goes out, how many go out? Maybe like 5 or 6. Instead of the whole string going down, you get a small section that goes down. Right? Series circuits are fine. They're the most basic kind of circuit. Christmas lights are, again, one of the most common ones, but they're not even that common anymore as that kind of circuit, unless you get the really, really cheap ones. You want to know the truth on that. You get the really super cheap ones that are like $1 a string for about 100 lights at Dollar General or Walmart, then yeah, you're probably going to get a full series circuit.
Just 5 bulbs go out. What is considered series parallel?
Yeah, I think that would probably end up as being called series parallel. Why? Because they figured out that if you could, how many of y'all actually ever wanted to try and go track down that one bulb in that string? I think every single one of us has sat there and said, okay, well, one bulb's out. I'm not going to go searching for that. Let's just trash can.
Spare bulbs.
They might give you spare bulbs. That doesn't mean you're gonna go looking for it. If you've got a 500 string of lights, you're not gonna go digging through 500 bulbs just to find that one that's burned out. It ain't worth the money. It's not worth the time most of the time. You're just gonna sit there, wad into a big wad, throw in the trash can, go buy another string.
You spend that on the toilet.
Huh?
I don't know, man.
Yeah. It's not even $10 anymore to get a string of Christmas lights. I can get a string of what they're calling fairy lights. You can get, those are the more expensive ones now because they're really tiny LEDs. Maybe $10, $15. The real true Christmas string lights, I think I've seen them for like 1,000 for $10, $20. It's not that expensive. It's not like when all of us were younger and that whole string would have cost you $50 for a string of lights. No, they're cheaper now. So we don't really use basic series circuits anymore. Why? Because if one goes down, they all go down. One of the things you can kind of think about in series is the basic electrical that runs our whole city, AC. Now, why do I say that's series? Well, because if the transformer goes out, it starts taking everybody out, right? So they are in, basically you're wired series parallel to the Alabama power. It's series because if the transformer goes out at one end, your whole street's done until somebody comes out and fixes it. However, if, let's say, somebody burned out all the bulbs in their house and they're down and out, does that mean anything to the rest of the street? No. So there's series in the fact that all our power comes from single poles. Parallel in the fact that we pull it individually from that pole. Just like your house is wired series parallel. I won't say it's wired series parallel, it's series parallel. Why series? Because you have one master switch that will turn off all things in an area, or one master switch that'll just kill the power to your whole house. It's called the circuit breaker box, right? Now, why is everything also wired parallel? Well, because if one bulb goes out, all of them don't go out, right? But they all go back to the same circuit breaker. So parallel is how we wire individual lights in a house. Again, that's how, if, let's say this bulb right here goes out, the whole row won't go out. It actually takes something else to do that. So, trying to think if there's anything else I need to cover on that. Good?
So in order to put 4 light bulbs in parallel, do all the wires go to that one source? Or?
Yes. So basic wiring of a series circuit looks like this. You have your source, and each load kind of runs along the lines of a train, right? Basically like stranded Christmas tree lights. If one load goes out, takes everything out. Okay? So it just goes one after the other all the way around. Versus parallel, which you have a singular source and each load goes back to that source. That's why each one of these lights runs on 120. Does that make sense? Okay. So technically your whole house is wired parallel. We'll go into something else on that later. Series parallel. The whole purpose of series parallel, and the great thing about series parallel is it kind of gets rid of some of the weaknesses. If one load goes down, the whole thing doesn't go down. You might just lose these two right here. In parallel, the bad thing about it is that if you short a load, everything else has to pick up. Let me go back one. So in series circuit, the bad thing about a series circuit is, as we talked about, Load 1 goes down, it takes everybody with it. Okay, load 1 goes out, your circuit's done. In parallel, it's not so bad if one load goes out. What is bad is what? Those of you that have taken intro or DC with me. No, even worse. This guy shorts out. Won't matter what the other loads are. All the current goes through that one load until you catch something on fire. So a short is a really bad thing to happen in a parallel circuit. An open, which is what happens when a light bulb burns out, is bad in a series circuit. Neither one is really that terrible in series parallel, because if one load shorts, you've got another one to pick up that same load and stabilize the circuit. Does that make sense? That's why series parallel is starting to become popular, is because if one goes out, kind of like the new Christmas tree lights, if one goes out, you don't lose the whole freaking tree of lights. You just lose what? 5 or 6, right? That's series parallel. It keeps the damage to a minimum. If I get an open, it's no big deal. If I get a short, it's no big deal. That's why a lot of things are starting to become more series parallel, just as a kind of protection. So pictorials. These use pictures to illustrate the system. Okay? It's just trying to show you the actual system. So you've got an LED and showing you the different resistors and the different, so you've got your power coming in from your transformers, and those are, if I remember right, capacitors. Wrong symbol for them, but that's me being picky. This is a pictorial. So what's the great thing about a pictorial versus if I just gave you a spaghetti diagram? Is that it's showing me this is what the actual thing looks like. Here's where you're going to put your wires. And that's great, right? Except, is my thermostat control switch going to be right next to my ignition switch? No, it won't. They're going to be on totally different parts of the car. But it shows me, oh, these wires right here go to this connection here, those go to there, so on and so forth. Okay? That's the great thing about a pictorial diagram. It shows me where my wires actually need to be. Does that make sense? So reading electrical diagrams, if you're looking at the wiring diagram, determine how the parts look, where they're located, and how they are connected. Okay? First of all, if you're looking at a wiring diagram, you need to make sure it's a wiring diagram and the correct diagram. What do I mean by that? Well, if you've ever been on a construction site, if you've ever seen the book of blueprints people give you with any machine, are all those diagrams wiring diagrams, or do you kind of have to dig for it? You got to dig for it. Make sure you're looking at the right diagram first and foremost. Okay? Then start trying to identify your parts. If it's a weird part, it might be listed in the legend, and then you have to go find it somewhere in the schematic. It's not a terrible thing, and it works pretty well for what it does. So once you've identified the part you're looking for, you start tracing that path to find where the problem has started from. It could be as simple as looking for a loose wire. Because what happens in industrial is wires do come loose. What do you have to do? You have to trace it down. What happens in pneumatics and hydraulics? Eventually a hose will crack or a pipe will crack. What do? You got to go run it down and replace it. Same kind of thing. So list possible solutions and look at the wiring diagram for any other possible solutions. Maybe you just need to jump it out. Jump it to somewhere else. The whole point of it is to look for, where's my problem? Where's the problem child? What is the solution for the problem child? Right? So if I've got a big piece of, well, let's say that one of my mechanicals over here goes down. I've got to start tracing that wire on one of those lines. I got to be real careful about, first of all, finding that wiring diagram, second of all, tracing it. And knowing exactly what I'm supposed to be tracing it to. Because if I just look at it, and I look at Spaghetti Monster, am I supposed to know how to work Spaghetti Monster? Nah. That's why you have diagrams. They help you find your way through Spaghetti Monster. So this is the schematic of a motor wiring. So you've got your 3 forwards, your 3 reverse contacts, you have your thermal overloads, and you have fuses on each load. On each one of these with a disconnect switch above it. Okay. That is the basic rundown of this. So the fuses are meant to do what? If this thing starts pulling too much current, what are the fuses going to do? They're going to do what a fuse does. It opens. It breaks itself so that you don't end up breaking your motor. If the fuses don't work, you have these thermal overloads. So if the motor starts overheating too much, if it's drawing too much heat, these guys open so that your circuit will break. Why? Because motors are made of copper wire and they're expensive. Not to mention they are really hard to replace sometimes. Those things are heavy. Okay. This is not called a schematic. This is a ladder diagram. Don't ever call it a what? It's not a schematic and it is not a wiring diagram. It is a ladder diagram. The other fond name we have for this guy is what is called a ladder logic diagram. So this one is usually called ladder logic. Anybody know what logic means, or what is logic? So logic is basically back up. There's several different kinds of logic. There are 3 main ones, and then there's the reverse of them. The 3 main ones, you have and, or, and not. And logic, that means that you need more than one thing to be true or your circuit will not work. I need this guy to be closed and this guy to be closed for this circuit to work. Does that make sense? You also have OR logic. I don't really have OR logic on here, but basically what OR logic is, it means that either one of these push buttons could be closed and the circuit would work. That's not OR logic on there, that's AND logic, but we'll go into that another time. And then NOT logic is generally the stop button. That's why it's called ladder logic most of the time. If you ever take motor controls, that's exactly what Rich calls it. That's what most people that deal with motors call it, because there's truly is a logic behind it. It's the best way to say that. Okay. So wiring diagrams and schematics. So wiring diagrams are supposed to show you what? Connections. Ladder diagrams just show you what? How is it actually, what is the way it's put together? Not so much how is it put together, in what order is it put together, I guess you could say. Does that make sense? Huh? Yep. How it interacts with each other. Thank you. All right. So these are some AC motors for what we're about to talk about. So this is Circuit 1 practice. This should be in your book. I'm not sure what page it is, but it is the back of chapter 4. So if all of y'all would please, if you don't have your own book, share with somebody else, please, or at least kind of everybody look at it. And I've got this as big as I can get it, honestly. Should be roughly page 55, I think. It might be 58. It's coming. Yeah. This is an older book, so sometimes the older books don't have the same page numbers. All right, so looking on page 58 in your books. Let's look at these questions real quick. What color would you expect to find connected to terminal S on the terminal board? Okay. So what's the best way we can check that? Well, we look for our terminal board. We look for S. So looking right at this guy right here, and then we look out, and what wire is it? It's white. Okay. All right, so what's the next question? What color wire should be connected to terminal C on the terminal board? So let's look for terminal C. What color is it? Where is it? Here's our terminal board. There's C. What wire goes to it? The black tracer. What does it, by the way, what does it mean to be black tracer? What does it mean by that? So wire is very interesting in the way that we've got it set up. Because generally it's a solid strand color for most wire. Just like, I can grab one of these. Just like this. We typically think wire is supposed to be one solid color. Yes? If it's got a tracer on it, what they've done is that on some part of the wire, they've run a stripe of color all the way through that wire. So that's what a lot of this stuff is that it's talking about, it's got this yellow, it's got a certain trace color to it. Okay? All right. It's got black tracer to it. The insulation on one wire in the circuit is colored white with a red tracer. What terminals should the ends of this wire be connected to? Well, it says here, it tells us white with a red tracer right here. It's pointing to this wire right here. So I'm going to start tracing it. And it goes down to L on our current relay. And it goes up to X. Does that make sense? So that's all just tracing that wire. The insulation, what colors are the wires going to the motor? There are 3 wires to that motor. Red tracer, black tracer, and white. Okay. Are the contacts in the control relay normally open or normally closed? So I guess we have to look for what is our control relay. Where is that? It's up here where it says control. Huh? And it is open, yes. allergies. Which terminal in the current relay conducts current to the run winding of the motor? All right, so that talks about which terminal in the current relay, that's this guy right here, current relay. Which terminal in the current relay conducts current to the run winding of the motor? Okay, so we have to look for the run winding of the motor. Well, we have a run and we have a start. So we have something that's got to go from one of these 3 points to my run capacitor down here. What is the color of that wire? And what terminal does that go to? It goes to M. All right. Which wire conducts current to the start winding? So we've got run, where's start? It's right next to it, right? So what connects start to this board? It is S. Thank you. Okay? Does that make sense, guys? Any questions on that particular one? What parts of this circuit are optional? No, not quite. There are 3 parts of this that are not necessary. And they actually label themselves as if required. You have your fan, because it says fan or fans required when they're required. And these 2 capacitors down here are not required when capacitor is required. Okay. If a fan is included in the system, is it connected across the incoming power line? The answer to that is, might want to check again. So tracing my fan, got one leg coming to X, I've got one leg coming to, I think it's Z there. Now looking at where my power lines are, they come in at Y and Z. You'll see that? So is the fan across the power source? No, it is not. Okay. Spin-off question. If we're using a start capacitor, what wire must be removed? We need to remove this jumper right here. That's a great test question, isn't it? All right. I won't torture you on this one anymore. Any questions before I move on to the next page? Anybody? All right. So this is the last page in your book, and it's another set of questions. So let's kind of go through these real quick, and I'll take roll, and y'all can go on for the day. All right. So looking at this, what colors are the wires leading from the contactor box? I'm sorry. I'm trying to get my brain to focus here. What colors are the wires leading from the contactor to the power contacts in the terminal box? So, I've got the terminal box here. Okay. This guy right here is my contactor. This is oil protection control, and this is the control with the motor down here. All right, so I'm going from my contactor to my terminal box. So what is that color? Everybody agree that it is what? It is black. So we're going from these power inserts down into the terminal box, and those are black. Okay. What colors are the wires going to the fuses in the terminal box? Okay. Everybody see that? Where are the fuses? That's these two things right here. You have a fuse panel. What's coming to them are these brown wires from this box up here. Okay. What terminals do the wires from the control connect to inside the terminal box? So what we're looking at here, so we're coming from control through this box into the terminal box. Where's that end up? Ends up terminal F1. Goes to terminal F1. Looking for color wire here. It's looking for what, where does it start and where does it go to? Okay. It's looking for where does it start and where does it go to? A white wire with a brown tracer connects the terminal M2 on the magnetic coil in the contactor. Where is the other end of this wire connected? So you start tracing this white with a brown tracer, and it goes to looking for, it goes to M in the oil protection control box. Jeez. What colors are the wires that carry the main power in this circuit? Yep, those are the ones that are black. Which incoming power lines provide power directly to the wires coming into the fuse panel in the terminal box? So we're looking at the fuses again. got two wires. Follow them up. One goes to the control box, that's this one right here. The second one is coming up to what? You'll see?
Directly to L2.
It goes to L2. It goes to L2. You'll see that? When contacts in the contactor are open, is power available at either terminal of the magnetic coil? Is power available at terminal T3 in the contactor?
Yes.
Which one? No? Should be M1. Because what you're looking at is the fact that this guy right here is getting power straight from L1. You see that? It gets power directly from L1. How many conduits enter the contactor in addition to the conduit in the incoming power lines? How many conduits enter the terminal box in addition to the conduit for motor wiring? So what we're looking at here, what is conduit? Conduit's the wire protector that brings it into a box. Now then, just to kind of look at it, that is conduit 2. You have a major one here and a small one there. How many has it got? It's got 4. What about this guy right here? How many has he got? He's only got 2. He's got that one and that one. Does that make sense? When you turn on the motor control switch, which terminal in the terminal box receives electricity? That is correct. All right. Y'all got any questions on how to read these schematics? Any questions at all, guys? All right. So it is 11 o'clock. I'll go ahead and let y'all go a little bit early after I do roll. So stick around for just a minute, guys. I'm going to get roll real quick, and then I'll let y'all roll. And no, I did not mean to do such a lame joke. Huh?